Guys, today we're going to do 2-3 part 1 continuity. We've been working with continuous functions, and in a continuous function would be a function where you can draw in one continuous motion. And so if we could draw our function without lifting the pencil, the function would be continuous. Today we're specifically going to talk about continuity at a point and continuous functions. So investigating continuity. We need to find the points at which our function f is continuous and the points at which function f is discontinuous. So first, over our domain from 0 to 4, our function is continuous, except at two values, except at x equals 1 and x equals 2, which we could clearly see in our graph. So we first need to look at the relationship between the value of the function at a certain point and the limit. So the limit and the value need to be equal in order for this to be a function, a continuous function. So we're going to first look at our two endpoints. So 0. If we look at 0, our whole function is happening to the right of 0. So we're going to take the limit as x approaches 0 from the right of our function f of x. And as we look at that, it is equal to f of 0. Excuse me. So at x is equal to 0, we are continuous. Now the same thing with 4. 4 is our other endpoint. So we're going to go from the left because our function is towards the left of 4. So the limit of f of x as x approaches 4 from the left is equal to the value of f of 4. Therefore, our function is continuous from 0 to 4, but we do not include 1 and 2. And the reasons we don't include 1 and 2 is because we have points of discontinuity there. So at x equals 1, we want to find the limit of f of x as x equals 1. So from the left, we're going towards 0, and from the right, we're going towards 1. Since our limit does not exist, we are discontinuous at x equals 1. And then we have at x equals 2. We find the limit of f of x as we approach x equals 2. So we have to go from both sides. And although our limit is equal to 1, f of 2 does not equal 1 because f of 2 equals 2, making x equals 2 discontinuous as well. So the definition of continuity at a point: if we have an interior point or a point on the inside, a function y is equal to f of x is continuous at an interior point C of its domain if the limit of the function as x approaches C is equal to f of C. And if it's an endpoint, the function y is equal to f of x is continuous at a left endpoint A or continuous at a right endpoint B of its domain if, first we're going to talk about left endpoint A, the limit of f of x as x approaches A from the right is equal to f of A. And now if we're a right endpoint, we need the limit of f of x as x approaches B from the left is equal to f of B. And if a function f is not continuous at a point C, we say that it is discontinuous at C. And C is a point of discontinuity of f. Example 2 is finding points of continuity and discontinuity. First, so we're looking for the points of continuity and the points of discontinuity of the greatest integer function. And we know that for the greatest integer function, this is what our graph looks like. And for a function to be continuous at x equals c, we know that the limit as x approaches c must exist and must equal the value of the function at x equals c. So let's pick a value I'm going to pick 3. Just going to label for us. So we are going to find the limit as x approaches 3 from the left, which is equal to 2. And the limit as x approaches 3 from the right of our function f of x is equal to 3. So the limit as x approaches 3 does not exist for our two-sided limit. So now if we talk broadly as n is any integer, if we are finding the limit of the function as x approaches n from the left, it's going to be n minus 1, or 1 less than. If we're looking for the limit of x approaching n from the right of f of x, it is going to be equal to n. Since these two are not equal, for all integers, our limit does not exist. Therefore, we have points of discontinuity at every integer. And just like we said, the greatest integer function is discontinuous at every integer, like we just proved. However, it is continuous everywhere else, because if we have the limit of f of x as x is approaching, say, 1.5, if we're approaching 1.5 from the left or from the right, we are still at a value of 1. And if we plugged into the greatest integer function, or int 1.5, that is also equal to 1. Therefore, we are continuous. Here we have a few different types of continuity, and really, more specifically, types of discontinuity. So we have a continuous function here, y is equal to f of x. Then we have the same function, but we have a hole at x equals 0. So the function in b would be continuous if we had f of 0 is equal to 1. But it's not continuous at x equals 0 because we have a hole. And then we have in C a hole and a different defined point. So this would be continuous if f of 0 was 1 instead of 2. But since our function is defined at 2, this is not continuous, or it is discontinuous. These are removable, and because each function has a limit as x is approaching 0, we can remove our discontinuity by setting f of 0 equal to the limit. In this case, we would have to set them equal to 1. And then we have discontinuities in these three graphs. So we have the step function here, once again, and at 0 we have jump discontinuity because we go from 0 to 1. And we have no way of saying that between the values of 0, that value of 0 should jump all the way up to 1. So that would be called a jump discontinuity. the function f of x is equal to 1 over x squared here has infinite discontinuity. And in our last function, in graph f, we have oscillating discontinuity because we are going back and forth and has no limit as x approaches 0. So it's oscillating as x approaches 0. If we are trying to remove a discontinuity, we can factor our denominator. By factoring our denominator, we know that our possible points of discontinuity would be at x minus 3 and x plus 3. So now I'm going to look at my graph. Oh, sorry for the glare. And we can see that at x equals negative 3, we have an asymptote. But at x equals 3, we don't, which means we removed our discontinuity. If we're removing our discontinuity, that means x minus 3 has to be a factor of our numerator. So I would use synthetic division. Since I know it's at x equals 3, I'm going to put 3 on the outside. For my coefficients in my inside, I'm missing the squared, so I put a 0 for my placeholder, negative 7 and negative 6. Bring down 1. Multiply and add. Multiply. Since I have a remainder 0, I know that x minus 3 is a factor. And this would be 1x squared plus 3x plus 2. And I can remove the x minus 3. So that we have a new simplified x squared plus 3x plus 2 over x plus 3. So if I take the function where I took out the x minus 3, which was our common factor in our numerator and our denominator, I'm going to find the limit as x approaches 3 of our new function, which would be x squared plus 3x plus 2 over x plus 3. And I would get 9 plus 9 plus 2 over 3 plus 3, which is 20 over 6, which is 10 over 3. And if I evaluated that, it would be equal to this as well. So since it's equal, we could say that the extended function would be g of x, where x cubed minus 7x minus 6 over x squared minus 9, if x does not equal 3, because this is still with that common factor. So that was our original function. But then if we could also define the x is equal to 3, because after we removed it over here, we found that the limit and the value are the same, which is 10 over 3. So if x equals 3, then our value would be 10 over 3. So we would be continuous at x equals 3. And the function g is called the continuous extension of the original function f, so that we could have the included value of x equals 3. Then we have continuous functions. So a continuous function on an interval, a function is continuous on an interval if and only if it is continuous